Linear regression is a very useful technique within statistics that allows us to investigate relationships between various measurements that have been taken during an experiment or during an observational study or any other similar investigation. So what we're looking to do with linear regression is to look at a system and to take a measurement which will be described either as a response variable or the dependent variable or some other name, and look how this variable of interest changes as some of the other settings of the system, the so-called explanatory variables or independent variables, change themselves. And we're trying to describe the relationship between these measurements using a mathematical formula and introducing a stochastic element rather than using a deterministic model. So to illustrate simple linear regression within R, we're going to take a look at the data set that's in the MAS, Modern Applied Statistics with S package. So the first thing we do is to make the package available in our session, and then we can type the name of the data set, which is rubber. So this data set is on information about accelerated testing of tire rubber, and there are 3 columns of data. So the first column is our response variable, which is the abrasion loss, and then we've got 2 other variables that we may be interested in plotting, and these are the hardness, and this is measured in what are known as Shaw units, and the tensile strength of the tire rubber. So the first thing that we would do with a data set like this would be to take a look at it. So we could plot the data, for example. So if we make the lattice library available for our session, and then we can do, say, an XY plot. Our Y variable is loss, an X variable might be the hardness, for example, and then we use the data equals rubber to indicate that's the data frame where our data is stored. So if we run that function and drag the window over here so it's in sight, what we could see is that as the hardness increases, the abrasion loss decreases. So it looks like there's a relationship here that could be described by a linear function. We could also do a similar plot, but rather than using hardness, we could use tensile strength. So we replace the hard with tense, which is the name of the column for that data, and then if we bring the graph up here, we can see that the relationship is slightly less clear-cut. There seems to be a decrease of abrasion loss with increasing tensile strength, but it's not as straightforward as with the hardness variable. So what we might want to do here is to fit a linear model to one of the variables. So if we try and describe the abrasion loss by the hardness, we use the LM function, which is for linear models. We start off with a model formula. So the loss is on the left-hand side, indicating it's in some terms the Y variable, the response variable, etc. And then to the right-hand side of this character here, the tilde is a series of names of variables. In this case, we've only got one, the hardness, or we can describe quite complicated models if we had that amount of information and it was relevant to do that. So if we run that function, we get a simple output. So we get the estimate of the intercept and the slope. So what we might want to do is save this to an object, so say mod1. As we're saving it here, we don't get any printed output, and then run the summary function, which is available for all types of models, and it might be customized to display certain information if you're looking at a particular type of alternative model. So there's a bit of information here. Got information about the residuals, so it's just summary information, and then a table of estimates, which we got up here for the coefficients in the model. So to work out the loss using this model, if we had 0 hardness, which would be hypothetical, then the abrasion loss would be 550.4, and for every unit of hardness, that abrasion loss will decrease by minus 5.33 units. So we've also got estimated standard errors for this model, t-values where we're testing whether or not the intercept and the hardness coefficient are 0, and p-values which are suggesting that actually they're not 0. At the bottom of the output, we've got some further information about this regression model to do with the residual standard error, and then if you want to use a multiple R-squared statistic and an adjusted R-squared statistic. So the f-test here is equivalent to the t-test, as we've only got one variable in our model. So once we've done this step, so we've fitted our model, we might be interested in looking at the diagnostics for this model. So the first thing we'll do is we will ask the base graphics to give us a 2x2 series of plots, and then we can use the plot function on our fitted model, and we'll just simply return the graph state to its original form, which won't change what we got in the output. And here we see we've got the 4 standard plots that have been produced by R when we look at a linear model. So in the first plot we can see there's some suggestion that at the higher fitted values we're not getting an equal spread in terms of the residuals. So the residuals are the difference between our model and the data that's been observed. Second plot is looking at a normal probability plot, which is one of the assumptions that's made when looking at a linear model. And here, because these points aren't falling particularly well on the dashed line, that's suggesting that the assumption of normality for the residuals is not ideal for this data set. So we might need to go further, either to consider adding more variables to the model, or potentially considering a transformation for our response, the loss measurement, to see whether we can improve some of these plots in terms of meeting up with the model assumptions.